Hi everyone, happy Wednesday. Welcome to Futureproof Your Planet, our sustainability masterclass series. I'm V, I'm a third year student of environmental science here at the University of Manchester. And in this series, we'll be exploring how science, engineering and fashion can help tackle some of the world's most challenging sustainability issues. In each session, we'll have an academic come in and share their expertise, followed by Q&A, and where we'll answer your questions. Today, I'm delighted to be joined by James.
Hey everyone.
Who will be speaking about chemical engineering.
I will indeed.
Yeah.
Looking forward to the questions.
Yeah. After the talk, we'll be back live to continue the Q&A and any discussions in the chat. And yeah, we'll grab a cuppa, sit down and enjoy the video.
Hi, I'm James Winterburn, a professor of biochemical engineering in the Department of Chemical Engineering here at the University of Manchester. Today I'm talking to you from our chemical engineering labs, and I'm going to talk about how we can drive the transition to sustainable bio-based alternatives to petrochemicals in order to future-proof your planet. You might not have ever thought about it, but last time you were washing your hair, you were using things called surfactants. So these are the molecules that actually remove the dirt and the grease from your hair. And at the moment, they come from fossil carbon, so from non-renewable crude oil. Industrial biotechnology is a really big field, but it's all about how we can use living microorganisms, things like the yeast that we use to make lots of food products, but rather than making things that we eat, making chemicals that we all use every day. This is really key, and we have this idea of wanting a future bioeconomy that reduces our dependence on crude oil as the source of all of the chemicals that we use every day. I'm really passionate about the role chemical engineers have to play in transitioning to a sustainable future, something that needs to happen now. I produce bio-based chemicals from renewable resources as alternatives to the chemicals that we currently get from crude oils. This is really critical because these chemicals are the ingredients in the things we all use every day. In particular, I'm interested in biosurfactants. So these are alternatives to surfactants that we get from crude oil. And surfactants are the molecules, the ingredient in cleaning products that give the cleaning action. They help remove dirt from a dirty plate, for instance. These are things that we all use every day, even if you've never thought about it. So they're in shampoos, they're in the sprays that we clean hard surfaces with. They're everywhere, they're ubiquitous. The problem is that when we produce surfactants from crude oil, these are non-renewable resources, and the surfactants themselves are non-biodegradable, so they persist in the environment for a long time. In particular, think about the way we use these products, it's for cleaning. So that means that these surfactants, they end up in water. And so aquatic pollution is a really big topic and not the only area where surfactants have an impact, but a really important one. And the really great thing is that we can use renewable raw materials. So we can use things like sugar and vegetable oil, and we can turn those into similar ingredients. So they still have this cleaning action, these biosurfactants, but they're biodegradable. So we avoid a lot of the inherent problems around using petrochemical-derived surfactants in consumer products. One of the ways that we can have an impact as chemical engineers and really future-proof our planet is around sustainable production of these bio-based materials. Back in 2018, I span out a company called Holiferm that's a kiloton scale manufacturer of these biosurfactants. Holiferm has very strong Northwest and Manchester in particular origins. So the co-founder of Holiferm, along with myself, is Ben Dolman. Ben was actually my first PhD student when I established my research group here at the University of Manchester. And he himself was a Manchester chemical engineering undergraduate. So this just shows how a Manchester chemical engineering education can really prepare you to go on, not only invent technology that gets patented, but more important than that, do what we call the translation. So take an idea out of the lab where we can actually make a difference and have what we call impact. So in the case of Holiferm, we now sell globally, all over the world. We're selling these biosurfactants for use in what we call formulated products. One of the key challenges when we look at using industrial biotechnology is efficiency by which we can produce. So one of the key challenges is cost of manufacture. So it's all well and good being able to make these alternative bio-based chemicals to replace petrochemicals with, but if we can't make them quickly enough or in sufficient quantities or at the right price, then they're never going to be able to enter the market. Okay, if I could make you the world's most expensive bottle of shampoo that was much more sustainable, that sounds nice, but the cost premium is really prohibitive. So one of the things that you really learn as a chemical engineer is a way of thinking. So how can we not just look at technical development of processes, but also do a couple of other things that are really important. One we call techno-economic analysis. So that is, given a process, how does it perform economically? Where can we improve so that we can reduce the cost of manufacture? Even more important than that, when you're thinking about future-proofing your planet, is sustainability and what we call life cycle assessment. Life cycle assessment and the tools and the way of thinking that you need are integrated throughout our undergraduate chemical engineering curriculum and is actually recognized as a key strength here in chemical engineering at the University of Manchester. What life cycle assessment allows us to do is answer a really important question. Is our new, novel, engineered bioprocess actually better than the standard petrochemical process? Just because we've done something that we think is quite clever in the lab doesn't mean that on an environmental basis, it is actually superior. So LCA, life cycle assessment, allows us to methodically and rigorously understand the life cycle impact of our process and the biosurfactants that we make. So we're interested in things like carbon emissions or global warming potential. It's how much carbon dioxide gets emitted per ton of biosurfactant we make, and lots of other impacts as well. The key thing here is this thinking allows us to then identify what we call hotspots in our process. So the bits, the stages, the raw materials that we use within that process that have disproportionately the highest impact. So that then allows us to prioritize and look at how we can further improve. And that's really what the research in my group is really focused on. How can we engineer efficient, sustainable processes through fermentation to produce these molecules, these bio-based chemicals that we all need. So through the research that we do here in the biochemical engineering group at the University of Manchester, really interested in making efficiently and engineering efficient processes for the production of bio-based molecules. This involves doing a lot of work around fermentation process development, but in dealing with problems that we're really well equipped to deal with as biochemical or chemical engineers, in particularly scale up. So when we produce biosurfactants in the lab, we do that at very small volumes. That allows us to develop the process. So like the technology that we invented here at the University of Manchester that we span out through Holiferm, having patented. The thing is, what we need is a process that is not only efficient at very small scale, but when we go to very large scale, so 20 cubic meters and beyond bioreactors, so in a real biochemical manufacturing facility, we need to make sure that the process actually performs at that large scale as well. Another great thing that you get in your education as a chemical engineer is an understanding of just that, process scale up. So how do we control the various important parameters? How do they scale when we make the volume of the fermentation bigger? Because unfortunately, not everything stays the same as we get bigger. So there's a lot of trade-offs that we have to explore. Manchester's a great place to study chemical engineering. We have a winning combination of world-leading expertise and excellent facilities that you get to use in your undergraduate teaching labs, through MM's dissertations, and lots of other opportunities as well. Thinking back to that bottle of shampoo that's currently formulated with petrochemicals, an education in chemical engineering and the thinking that Manchester provides will uniquely position you to be able to replace those with bio-based alternatives and future-proof your planet.
All right, so we're back and we're here with your questions. So James, what would, first question, what would using biosurfactants, increase the price of these everyday items? How would you go about that?
Yeah, so I think that's a really great question, because if you're not careful, And in general, we have all these like great solutions for things, but ultimately in a technical sense. But at the end of it all, if I can make you a bottle of shampoo that's 3 times the price of your current shampoo, that's not going to solve the problems. It's not going to actually enable us to replace crude oil derived chemicals with the biodegradable, bio-based alternatives. So the whole challenge and where chemical engineering comes in is how do we create and refine, make better the production, the manufacturing process to really allow us to make a biosurfactant that is competitive on a what I would call a cost performance basis, which means it performs better and costs the same or less than the petrochemical. Only if we get there can we actually do what we want to do, which is replace crude oil derived chemicals with bio-based alternatives.
Yeah, really interesting. And it's interesting that you bring up the manufacturing, because someone in the chat asked which catalysts can be used in the process.
Yeah, so this is a bioprocess. So by that we mean we use living microorganisms, so cells. So the cells themselves are the biocatalyst, and they do the hard work of turning a sugar into a bio-based chemical like a biosurfactant.
Yeah. That's really interesting, actually, like, genuinely. I think having that kind of like biology and engineering kind of fused together is somewhere that I think needs to be pushed towards more in the future if we want to have a sustainable planet. So we've got a 2-part question coming up now. So part 1, what other sustainable chemical alternatives are scientists developing in the lab now that, in your opinion, should deserve more attention?
Wow, okay, that's a one that makes me think. So in terms of what's been developed in the University of Manchester and beyond, there's a whole host of things. So some examples off the top of my head, we've talked about biosurfactants a lot, biopolymers. So that's something I also work on. So plastics, we all know about kind of the issues with microplastics, accumulation in the environment. So again, a biodegradable plastic. People work on fragrances and flavorings. People work on a whole host of things. Medicines is another big area, so biotherapeutics. I could go on and on and on. I think the point is there's a whole host of examples. And almost anything that you can think of, we could probably find a way of replacing. The question is, does it make sense to or not?
Yeah,
and the answer is, it depends.
Yeah. And then, so part 2 of the question, what is the time span like for you to actually get lab-developed products out on a global scale? What are the success rates?
Yes, that's a great question. So success rates is really hard to give a proper quantified answer on, because when you talk about commercialization of research, translation, spin out, that by definition is high risk. So I think it's actually more about the number of these things you do than the success rate, because the success rates are low, because it's really hard to get something all the way to market. Now, the example I spoke about in the video of Holiferm, so we spun that out of my research group, Ben and I, back in 2018. Where we are now, we manufacture, we distribute and sell globally. So, in that time period of approaching, 7-8 years. So, and that's pretty quick.
Yeah. Honestly, really impressive stuff. Really, really impressive. And I think it's really interesting, just touching back on, what's the future of biology-based products. As an environmental science student and obviously as an engineer, where do you think kind of the sustainability and ecology kind of side of what something that I'm studying could kind of interact with more of a lab-based engineering, kind of more mechanical side of things? Where do you think that could overlap?
Yeah, so I think if we go back to briefly to one of the other questions, it was about what can you find alternatives to, so what petrochemicals can we find bio-based alternatives to? And my answer is sort of, well, a lot of different things. I think you're going back to the question you've just asked now, what you need is a prioritization and some direction. So if we understand what some of the big challenges are, we can't solve them all immediately, all at once. So you need to do some sort of prioritization. And so someone like yourself who understands far better than I do some of the environmental challenges and how they are in the nuance of them, so how they're interrelated, how we can actually go about solving them, or what a solution might need to look like, that can then inform the engineering as well. as we kind of work through a solution. Because if we try and do everything all at once, the risk is that we are spread too thin and we achieve nothing.
Yeah.
So you need a bit of ranking and prioritization. It's like, I suppose, with the biosurfactants. We've got, through Holiferm, we've commercialized, we've got a molecule. We want more of, not just more biosurfactants, but why not just be a broader bio-based chemicals manufacturer?
Yeah.
So why stop there? But you need to build it up a little bit. Whilst equally, I'm not saying we can just sit back and wait. It's about prioritizing and picking where you go.
Yeah. One step at a time, right? Yeah.
Yeah.
And we've got another question. Do you think biosurfactants could completely replace synthetic surfactants, or will they just complement them?
So the short answer is yes. There's nothing in my mind that prevents us from completely displacing petrochemical surfactants from the market, especially in home, personal and laundry care, which are big consumer, fast-moving consumer goods segments. The complexity there is that some are easier to replace than others, and you need different molecules that do different things. So when we talk about these formulated products, there's lots of different surfactants in them that do different things. So we're not quite there yet, but ultimately that is the aim, and there's nothing stopping you from doing that. There's challenges for sure, but if you don't have that vision that says we're going to replace everything, then you'll never get there, right? So you need that level of ambition, and then you apply your expertise and build a group of people to do that.
Yeah, of course. And I think this will probably be our final question, or penultimate question. What microorganisms are commonly used in the production of biosurfactants?
Yeah, so it depends how you approach it, but in general, this is a general answer, yeast. So lots of different types of yeast. So like we have baker's yeast, which is called Saccharomyces cerevisiae, is its kind of proper name. So baker's yeast that we use to bake bread. Similar things to that, but different types, different species of yeast are the most common biosurfactant producers.
It's really cool how you could just find little pockets of engineering and science everywhere you go. I think it's quite good how we can kind of get from the wider world into something so productive and so ambitious, like you said. What would you say if you had to give advice to the people at home about getting into chemical engineering and studying engineering and your journey there?
Yeah, so I think that the great thing about chemical engineering is it gives you this foundation and this way of thinking. So that you get all of the technical things that you need to know, but this way of thinking goes beyond that a little bit. So being able to understand processes, whether they're a chemical or a biochemical process or something totally out of this kind of standard chemical engineering world we're talking about. But that way of thinking is really powerful. It helps you approach problems in a certain way that's really, really quite powerful in my opinion. I'm biased because I'm a chemical engineer, but I think that as a way of positioning yourself to look at sustainability challenges and being able to address them and future-proof your planet, then I think that's why not chemical engineering would be what I'd say back.
Why not? Yeah. And just a few quick questions. Is A-level chemistry required to do chemical engineering?
No.
Good answer. And can we do our own projects in first year in free time in university labs?
Not typically in first year. You do labs and you're guided. Later on in the fourth year, if you do an MEng, then you'll do a dissertation research project where you have more freedom. Because you're not free to do whatever you want, but there's more freedom to explore and work on a research topic.
No mad scientists running around Manchester, hopefully.
But we can be creative and think and innovative, but within some reasonable.
Of course. Yeah. Okay. Well, that concludes our Q&A section. Thank you so much for joining us today on Futureproof Your Planet. A big thank you to James for joining us today, and for you guys at home for sharing your questions and your thoughts and insights. Any questions that don't get answered will be answered later on. And for thanking you to come joining us here, you'll get an email certificate for your participation that you can use on your UCAS or any CVs, so that you've come and joined us today. So please make sure you join us again. Keep an eye on your inbox, and don't forget there's a few more talks coming your way. Thank you once again, and we'll see you at the next Futureproof Your Planet event.